This robot learned to balance on its own using AI and reinforcement learning. While balance bots are nothing new, if you follow along with what I'm about to show you, you'll see how to use reinforcement learning to teach the bot to balance itself. Most of the major robotics research companies and universities are now using RL to create robust control schemes that can handle a wide variety of environmental factors, even if they weren't seen in simulation. In the previous episode, we saw how to import a set of CAD meshes into the MuJoCo simulator and how to specify the various physical parameters, like the moment of inertia for each of the bodies. This time, we're going to develop a gymnasium environment wrapper for MuJoCo and adapt the CleanRL implementation of PPO to train our bot to balance on its own. Note that we'll be working entirely in the simulator with Python in this episode. We won't deploy the agent to the real robot until the next episode. Let's get started. I'm going to gloss over many of the fundamental concepts of reinforcement learning in this video. To get a better understanding of those concepts, I highly recommend watching my Introduction to Reinforcement Learning video first. My goal for this series is to demonstrate the high-level frameworks and techniques for creating useful agents for robotics. As a quick refresher, let's go over the basics of reinforcement learning. Our system, or robot in this case, will periodically produce an observation vector consisting of 4 values. The IMU will give us the pitch, or how much the robot is leaning forward or backward, how fast it's pitching in one of those directions, and the angular velocity of each of the motors controlling the left and right wheels. This observation is sent to the agent, which is our decision-making code. The agent is responsible for taking in an observation and deciding what action to take. It's the part of the code that gets automatically updated during training, and it attempts to make decisions that maximize total rewards received. Once the decision is made, our code will turn that into some action. For a device like our robot, that means controlling the drive motors. This causes the robot to move, which then affects the state of the robot, generating a new set of observations. This process then repeats over and over again. Note that everything that's not the agent is considered to be the environment. This includes the robot chassis, wheels, floor, the microcontroller, the code that generates the observation vector, and the code that turns the decisions into actions. During training, the environment is also responsible for generating a numerical reward that's sent to the agent so it knows how well it's doing. Designing the reward function is one of the most important steps in reinforcement learning, as it shapes the agent's behavior. We're going to use this reward for now. Note that this is computed at every time step, which is 5 milliseconds for this project. We'll start with a simple alive bonus, which just rewards some simple constant for having the bot not tip over. We then subtract some coefficient a times the square of the pitch. Assuming 0 radians is perfectly upright, we want to penalize the robot leaning beyond that. Next, we subtract some coefficient b times the square of the action taken. In this case, we simply sum the squares of the actions chosen by the agent. This penalizes jerky motions and encourages small, deliberate movements in the motors. Note that we have access to information in the simulator that we might not have on the real robot. This might be things like the absolute position of the robot or its heading. This is known as privileged information, and we can use it during training. We'll use the absolute position of the robot in the X and Y plane to penalize the agent for moving off the origin. We'll also use the privileged yaw rate rather than relying on the IMU gyroscope to penalize turning around the Z-axis. Altogether, this should encourage the robot to balance and stay near the origin without turning. Farama Gymnasium is the gold standard for creating environments for reinforcement learning. It comes with a number of pre-made environments, including basic control schemes, simple robots for MuJoCo, and Atari games. However, we're going to create our own simulated environment in MuJoCo for our balance bot, and we will wrap the control for that environment using Gymnasium. That gives us a common set of classes and functions our PPO algorithm can call to interact with the environment. If you open up the GitHub repository that we've been working in, go into Workspace, go to Software, and go to O2. This is the episode we're working on. Because the environment is going to be modified as we go forward with the series, I'm going to keep the environments in their individual episode folders. So let's open up this environment and take a look at it. We import some standard libraries that we'll be using. We also need to import Gymnasium. This is what allows us to create that wrapper. And lots of RL algorithms know how to interact with this kind of wrapper for Gymnasium. We also need NumPy, and we need MuJoCo for our simulator, just like we saw in the previous episode. To create a custom environment that wraps up our MuJoCo simulator, we're going to create this class BalanceBotEnv, and it is going to inherit from gym.env. So it's going to inherit the Gymnasium environment. We're going to define some metadata here that's mostly just used for rendering in MuJoCo, and then we create our constructor here with a number of parameters that we need to set. We specify where to find the MJCF file, how many steps we're going to run, if we're going to render, none means don't render, adjust the alpha setting for our complementary filter. We're going to make sure that our sensors and actuators, those names line up with the names in the MJCF file. And we have some coefficients that affect the reward function. And finally, we specify how much the robot can tip before the episode is considered over. And we're going to specify that at 30 degrees by default. We set all of this up by taking those parameters and assigning the values to class fields so we can access them in other functions. We also define our observation space. Notice that Gymnasium uses this box or spaces.box to define what this looks like, and we're just defining values between the low and high here. So the observation space is going to consist of pitch, that can be between -pi and +pi, the pitch rate, which can be between -20 and 20, that should be radians per second. We have the left and right wheel velocities, and those go between -50 and +50 for each of the wheels. We probably won't reach those rates, but that is the size of the space that's available. We store those in this box, so you notice we give it the lows for the space, these 4 dimensions that make up the observation vector, and then the possible highs, and because this is a continuous space, values can be between the lows and the highs. We also define our action space, what the robot can do, or what the agent can tell the robot to do. Similarly, we have to define NumPy arrays, and this is 2 dimensions, which is the left wheel torque and the right wheel torque. Remember, these should be normalized, as neural networks like to work with normalized values. So we're going to go between -1 and +1 for both the left and right wheel torques. Once again, we use this spaces.box. And if we scroll up, you can see we are importing that from Gymnasium. So let's go back down. So with our observation and action spaces set up, we go ahead and save the coefficients to some class fields. We save off the threshold, number of steps, initial pitch state. So we set these fields to act as globals, but more class fields that can be recorded between different steps or different method calls. We define an internal function called getObservation. We're going to use this in reset and step. To calculate this, we first read the raw IMU sensor data. We get the pitch according to the accelerometer by using a little bit of trigonometry, and we use the complementary filter to combine the accelerometer and gyroscope data to get this pitch value. We also read the wheel velocities from the sensors or the encoders, and we construct our observation vector here that gets returned. Reset is one of the required methods for this custom environment, as according to Gymnasium. Notice that we call the parent class reset function here and set seed to seed. We just pass that through. So that resets any seed we might set for randomized variables. We reset the simulator so that the robot returns to the origin upright. We reset the pitch, and we randomly set the angular velocity so that the robot starts tipping slightly in a direction so it learns to recover. This is the very first form of domain randomization we're going to be introducing here, and it's going to persist through the rest of the series, where we are randomly sampling some initial state value whenever the episode restarts. We also update the state of the robot so it actually goes back to The center point is upright and is given this essentially a push in a rotational direction, so it starts to pitch around its axles. We're going to reset our step counter so we can record that, and then we're going to return an observation from this getObs, so we call that function. Next, we take a step. So for each time step, this function is called. So the first thing we do is control the motors. So notice for step, we have to be given an action. So the agent outside of this environment determines the action, passes it into step. Step then takes that action. It's responsible for taking that action, advancing the simulator by one step, and then getting another observation. So that's what this step function in a gymnasium environment must do. So it must perform the action, advanced simulation, or whatever else you're using by one step, in this case 5 milliseconds, and then get that observation. We are going to return that along with some other information. We also need to generate a reward signal for the agent. For us, we're going to take that alive. So if we come down here, here's that alive bonus. We're going to penalize if it's pitching off of being upright. In this case, we take our coefficient that we set in our constructor, multiply it by the pitch that we calculated, and we're going to square that value. So it essentially works as an absolute value, and also it penalizes it more for more pitch. We have an action penalty. So this is going to help penalize jittery motion, so the robot doesn't just try to jitter back and forth to stay in place. We have our coefficient for that, and we're going to take the two actions that we had here, we're going to square them and sum them together to create one value. So the more torque we're asking of the motors, the more the robot gets penalized. So we're trying to teach it to take little actions to stay upright rather than just bouncing back and forth. We can also penalize the position, how much the robot moves off the X and Y. Note that this position data we get from these QPOS, or Q position. This is the simulation state, in addition to QVal, which we're going to show in a minute. These are values that are only available for training. We're getting them from MuJoCo, and we're saying how far away is the robot from the origin. This is known as privileged information because it's not something we would have during deployment or in a real robot. We can look at the world and say, hey, where's the robot in that world? And we can get that information very easily. We're going to use that information. We're going to square those to essentially get absolute values and punish positions off the X and Y more, sum those together, and multiply by our coefficient. We also want to penalize our yaw rate here. So we have our yaw rate that ultimately becomes part of our yaw penalty. This comes from this QVal, or Q velocity, that gives us information about the robot body in space. And this is a velocity. So index 5 in QVal is a measure of how much the robot is turning around the z-axis. So we're going to take that absolute value, we're going to multiply it by our coefficient, and that becomes our yaw penalty. So we essentially just sum all of these together. So any bonuses are positive, any penalties are negative. That becomes our single value reward. We also need to check if the episode has been terminated. To do that, we just see if the robot's pitch is greater than our tip threshold. So we're going to convert our 30 degrees to radians, compare those, and say if it has terminated. That means if the robot has tipped and if it has essentially failed what it's intended to do. Truncated means the episode ran longer than the max allowed. And so while the robot didn't fail, we're going to reset the episode back to the beginning so the robot can train from a new pitch rate that we impart on reset. And we can say truncated, and we return those as true or false values, these Booleans. So we return the observation, the reward that the agent can use. We have terminated to determine if the robot fell, or if we truncated, meaning we hit the maximum number of steps allowed. There's other information we can return here that Gymnasium expects, but we're just going to return a blank here. You can return this extra information for things like logging if you want to. The other thing we have to define is this render method. This tells the simulator, if you have one, how to render. So we're first going to check if render mode is set to human, because that's what MuJoCo expects. If it's not, just return. Essentially, we're not going to render anything. So if it is set to human, we're going to create the viewer on this first render call, set our camera like we did in the previous episode, and we're just going to say update the viewer. So we just sync it like that. Finally, we have to have this close method, and all we're going to do is just clean up the viewer. So if the viewer exists, we're just going to close that out. Before we write our PPO algorithm, let's make sure that our environment works. From a command prompt, probably WSL if you're on Windows, navigate into the Reinforcement Learning for Robotics repository that we've been working in. Go ahead and run the Docker image. Once that is running, navigate to localhost :3000 on a browser. This should take you into WebTop. Let's open up Jupyter Lab. Let that run. Go into Software, go into O2, then open up Environment Test. We're just going to run through these cells to make sure the environment works as intended before developing a reinforcement learning algorithm. So we need to import this environment checker, and we're also going to make sure it works and fires up the environment here. So Shift-Enter to run the cells. If you're working in another folder, you would need to append this here, but we don't have our environment in a separate ends folder anymore, so we can actually probably get rid of this. So we're just going to import this balance.env, which is the environment we just looked at, and import that class. So Shift-Enter to run that. We're going to set the path of our MJCF file, as we did in the previous episode, and set a seed here, so any randomization should work for you as it does for me. It's repeatable. We're going to initialize the environment by calling the constructor here, and we're going to print the observation and action spaces that you can see here. We're then going to use Gymnasium's built-in environment checker, which is going to fire it up and do a few tests to make sure everything works. And it looks like it comes up. We get a warning, but that's okay. As long as this returns with no error, you should be okay. So we can close that down. Then to use the environment, we're going to reset it by calling env.reset. We pass in the seed. We can print the first observation we get. You can then take a manual step by calling env.step here and passing in an action. In this case, there is 0,0, which is essentially perform no action on the motors. And you're going to print the observation vector, the reward, whether it's terminated or truncated. Then we're going to test the random policy. And this is what taking steps inside of the learning algorithm looks like. The first thing we do is reset the environment. Then we take 200 steps, that's time steps, each one is 5 milliseconds. We're going to take the start time here so that we can wait in order to make sure it's exactly 5 milliseconds so it looks correct. And like I said, this was 2, that needs to be 5. We're going to choose a random action, and we get this by sampling from our action space stored in the environment. We're going to take a step with that given action. So who knows what the robot's going to do? This is just a random policy. We're going to get that reward. We're going to accumulate the reward. We're going to render it in MuJoCo. We're going to show if it stopped or truncated. And we're going to make sure that it matches up to 5 millisecond time steps. This needs to line up with the time step given in the MJCF file. Feel free to get rid of this, as we're going to do for actual training, so that it runs as fast as possible. All right, let's run this. And it looks like I closed down the environment. So I need to rerun the environment up here. So that should start it. And then if we run it, there we go. And then you can see the robot just tipped over. You can see that it ran for 68 steps. You see the final observation and the amount of reward we received from those 68 steps. That's the total reward. I'm going to run that cell again, and you can see the robot kind of just doing random stuff. And it's mostly not making it very far. So that's what we need to accomplish with our reinforcement learning algorithm, is to have the agent update such that we're not performing random actions. Instead, we are choosing the action that tries to maximize our rewards, or in this case, keeping the robot upright. When we're done, we can call this environment.close, and that closes out both the wrapper, which includes closing out the simulator. Knowing that our environment works, we are ready to develop our reinforcement learning algorithm. Proximal Policy Optimization, or PPO, is one of the most popular learning algorithms used in RL today. It was developed by OpenAI researchers, and the paper was published in 2017. If you'd like to dive into the math behind PPO and found in the paper, I highly recommend working through the Sutton and Bartow textbook or taking an online course that uses it. I also have a blog series that briefly goes through this math building up to PPO if you would like the compressed version. PPO uses an actor-critic architecture, which involves 2 functions. The actor takes in an observation and outputs which action to take. Note that this is the policy used by our agent. The critic takes in the same observation and estimates the expected total reward from that point forward. This estimate is needed for updating the actor, which tries to make decisions based on what it thinks will maximize these future rewards. In deep reinforcement learning, both functions are typically neural networks, since they need to handle nonlinear relationships and have trainable parameters. These can get pretty complicated, but I found that simple 3-layer dense neural networks work pretty well for our simple BalanceBot project. As part of his research program at Drexel University, Costa Huang created CleanRL. It's a set of reference implementations of various reinforcement learning algorithms, all written in Python. We're going to take the continuous action version of PPO and modify it for our own needs. Back in VS Code, let's close out of our BalanceBot environment. If we go into the RL folder, this is going to be shared among a lot of our different episodes. We're going to find PPO Trainer. This is the CleanRL version that I have modified for our uses and documented to hopefully help you understand what's going on. I'm going to skim through this because there are, I don't know, about 1,000 lines of code here, so we're not going to go through each one, but feel free to read through the comments to get an idea of what's going on here. So the first thing we have is this configuration. It's just a data class that stores some data for us, and this is how we set up PPO. We're going to be using some sensible defaults here to try training. Some of these will be modified later when we go to do things like modify the environment, domain randomization. But for now, we're going to set up things like where we save the model. I'm not going to be using weights and biases. That's for tracking. I am going to be using things like saving the best model at various intervals so we can come back to a good model, because you will find during reinforcement learning, oftentimes you see the agent performing well and then suddenly performance just drops. And we can always go back to a previous model if that agent worked well for us. We're going to say where to save that. We are also going to define our architectures for the actor and critic. In this case, 2 hidden layers seems to work pretty well. I'm going to default to 64 nodes per hidden layer, but we will change this throughout the series. I find that starting lower for easier tasks works better. And I've discovered that you can go up to 64 by 64 or 64 nodes in each layer and still have performance be fine. It takes about 2 milliseconds to execute from raw C code on the ESP32. So that's well within our 5 milliseconds, or meeting that 5 millisecond time step deadline. It has a specified initial environment here, but we will change that. We have total time steps per training phase. We're going to change that as well. We have our initial learning rate, although we do use annealing, so it lowers that learning rate as the training time goes on. We can specify a number of environments. We can do parallel environments if we want to. We'll actually increase that to like 4 or 8 during the episode. Gamma is important for the discount factor in reinforcement learning, so 0.99 seems like a sensible default. Many of these I am either getting from CleanRL, what the initial or original code had, or doing something like asking Claude for suggestions for sensible defaults, putting those here, and then we can change those as we play around with the different hyperparameters when we go for training. We can also specify the number of mini batches, how many times to update the policy during the actual policy update portion after capturing some information about an episode. And then here's some PPO specific information. I won't dive too deeply in here, but this affects how much the policy or either the actor or critic can be updated. You don't want to take too large steps updating those neural networks, or you might overstep a maximum, in which case the agent will not perform as well as intended, or you don't get a good value estimate from the critic network. So a lot of these are just sensible defaults from CleanRL, and we're just going to be using those and tweaking them as needed. But I found that these defaults for things like clipping and entropy worked very well. The agent itself consists of the actor and critic networks, but notice here that we are inheriting from the neural network module, so nn.module. If we scroll up, you can see comes from PyTorch. So that's an area of PyTorch that we're inheriting, and we're going to be building networks based on that. To initialize our agent, or to instantiate an agent object, we're going to call the superclass, so that PyTorch module class there. We're going to get our observation action sizes. We're going to use that to build our MLPs, multi-layer perceptrons, or the neural networks, one for the critic and one for the actor. So if we go and find that build MLP, let's see, to right-click on that, go to definition. So it's just outside of any of those classes, just a regular helper function here. It just reads through the number of hidden layers and nodes per layer, builds the neural network using PyTorch, and just returns a dense neural network. So our agent only supports dense neural networks where the two hidden layers have the same number of nodes. Feel free to play around with this. There is a lot of research that uses different types of neural networks, things like convolutional neural networks or even transformers, and you have to really mess with the training algorithm to get some of those to work, but this is where you could try different architectures here. All right, so back to our agent, we have an actor and a critic. After we've initialized or instantiated the object, something to understand about PPO is that the actor will output a probability distribution of actions, not exactly a deterministic, hey, you should perform this action, but it gives you this probability curve. And when you're exploring, you should choose from that curve. And then ideally, the action or that curve gets narrower and narrower to become more deterministic. So this allows you to control how that works. Basically, how much do you explore in the beginning versus exploit the deterministic actions in order to maximize your rewards. Getting a value from the critic network involves just sending an observation vector and doing a forward pass with the critic, and then you return that result. So remember, the critic takes in an observation vector and gives you an estimate of the value from that particular state or observation. You can also get action and value. These all come from the CleanRL implementation, these function names and initial definitions. So we take our observation vector, we do a forward pass through the actor neural network, we get that action, or the action mean, because remember, it's a probability distribution. We calculate the standard deviation from that probability distribution, and then we can construct those probability distributions directly using this normal class here. That's something that gets imported from PyTorch, as you can see up here in our imports. Scroll back down. During a rollout, or in other words, simulating and seeing how the robot performs with a given policy, we're just going to sample from that probability distribution to get the actual action, and then we return that. We also return some other information along with the value predicted by the critic. We will keep our training results together in one data class, so it's easier to read. And then we have our module level functions, so these are outside of classes. We have make environment. This is something we saw when we were testing our environment. It just sets everything up. Notice that we're returning this thing called a thunk here, which is essentially a callable function. So you can call this function to get this function that can then be used to create your environments. In other words, we're creating a factory function here. We're going to be using orthogonal weight initialization. This is very common to PPO. You'll find this used over other types of initialization if you're coming from the machine learning world, where you might have LeCun or He initialization. This version works a little better, so we're just copying this right from CleanRL. We already looked at building our neural networks. We have a function in here that exports an actor. Remember, the agent consists of an actor and a critic. All we're going to do is strip out the actor. We're going to rebuild that MLP. We're going to apply the weights. We're going to load the model, apply the weights to that same architecture, and then we're going to export that to an ONNX file. This is useful for deploying to other boards, especially where you have ONNX runtime available to you, so things like Linux. But then in the next episode, we will look at actually taking this actor network and exporting it to not just ONNX, but also raw C code, since it's a fairly simple 3-layer neural network. I also have this helper function in here to export your TensorBoard plots to CSV files. This was useful for taking those comma-separated value files, uploading them to something like Claude or your LLM of choice, and having it look at what's going on in training to give you some feedback. So this is an automated way to do that, but I also always recommend not blindly trusting the AI output and looking at the graphs in TensorBoard yourself to try to understand what's going on with training. We can also evaluate the agent. So we give it an agent, we tell it how many episodes it needs to run, the configuration that we created, this is that PPO config we looked at, and then how to create those environments. And it just runs the agent without doing any training or updates and tells you how well the agent performed. This is also a good way to run this, and you can watch the agent do its thing with the balance bot in MuJoCo since you get to see it in real time. It will figure out how many steps it needs to perform per episode. It will run through those. This is very similar to what we saw in the test where we run an episode. In this case, it's running multiple episodes and it steps through each of those episodes. You can see here where we take each episode and we perform that step function that we just saw in our environment. It collects the rewards and tells you the total reward per episode. So ideally, the higher, the better for this episodic reward value. Ideally, you'll want to set step limits for each episode so it won't run forever for projects like this where the bot could balance forever. So at some point you want to stop it, or if it tips, you'll say that it failed. Once we're done, we put the agent back into training mode so it can do future updates. You'll see that in curriculum learning where we will train for one phase, evaluate that phase, and then move into the next phase for another set of training and evaluation steps. Finally, we have our big train function. This is where all the magic happens with PPO. So we pass in our config, we pass in our environments. Note that the original CleanRL implementation had a way to create an environment in here, but because we're using MuJoCo, we generally want to create outside of this module and then pass those in. We can also pass in an agent that we have created. We set up how to configure training. We assign a name for the run. So this is going to determine which folder the run stays in for looking at TensorBoard and also loading the best model from a given run. A run is any number of episodes for however long we specify, and hopefully the agent gets better during that run. Note that we can have multiple environments in a single run, so they can run in parallel. Keep in mind that how we've set up MuJoCo, or MuJoCo by default, only uses the CPU, so I recommend sticking to something like 4 or 8. Take a look at the number of cores you have available in your machine and in your Docker container. So I'll be using 4 or 8 cores or 4 or 8 environments for most of this training. I find if you go over that, you don't see many benefits just because the multiprocessing isn't there. If you do, however, want to try MuJoCo with GPU acceleration, you will need to put in a different backend. I think there's a JAX version that will allow you to do MuJoCo with GPU acceleration, but we're going to leave training on the CPU only for this series. For most of what we're doing, we're going to be passing in environments, but I tried to leave in building environments inside of this function to make it work like CleanRL. I didn't enable weights and biases for logging different experiments, so you can ignore this for now. We're going to initialize a log for TensorBoard. I did use TensorBoard because I find it very helpful to see what's going on because a lot happens in PPO. We're going to initialize our checkpoints and we're going to seed all of our random number generators. I think I got them all here so that when you run through the code like I did, it should produce the same or similar results because these are all seeded with numbers for the pseudo-random number generator. PyTorch wants to determine if you are using a CPU or GPU, which they call CUDA here because CUDA is their backend for talking to a GPU. Ideally, this should all be CPU for this particular container that we're working with, but I guess in the future, if I get MuJoCo working with GPU, we might be able to update that here. And then training or updating the neural networks with PyTorch can happen on the GPU in addition to simulation. Here's some basic checks to make sure that our environment's going to work for us. We're going to create a new agent, or if we passed one in, we're going to use the old one. This is what allows us to do multiple phases where we train an agent in one phase, pass it to the next phase, make some modifications to, say, the environment, and then continue to train using that same agent. We're going to create a new optimizer for optimizing our neural networks. We're going to allocate a bunch of tensors for storing stuff for those neural networks. We'll initialize our training state, like our step, our timer, the first observation, and so forth. Then for each iteration, we're going to run all the environments for the number of steps provided. So you can see our iteration here. Here's where we lower the learning rate over time, known as annealing. A rollout, remember, is just running our simulated robot for a number of steps before trying to update the actor and critic. I guess it could also be in the real world if you're not using a simulation. But a rollout is just perform some number of episodes and collect data on what happens so we can update our neural networks in order for the agent to hopefully do better next time. Here's where we pass in our observations. So we get our observation for each step. We pass that into get action and value. That gives us the action value. We're going to turn those into actions to be performed. So remember that those get sampled. We're going to log those in this giant array here, addition to our probabilities. Then we're going to perform those steps on all environments. So you can see environments.step. So if we have say 8 different environments, we're going to perform step on each of those environments. That's what we have here. We're going to see if the environment was terminated or truncated. Basically, the environment ended. We're going to log those rewards. We're going to get our next observation and save if it's done for the next time through this. If we're using custom environments, we're going to render the first environment, assuming that the render mode for that first environment is human. So we're only going to watch the first environment train. If we have 8 environments, the other 7 will be working in the background, just you won't see them. When an episode ends, we log some information to the TensorBoard writer that we've set up here. So that's this add scaler. We just log episodic returns and episodic lengths to TensorBoard so we can watch that happen. In this part, we turn off gradient tracking because we just want to perform some evaluation. We use information from the critic to predict these next values that we use to predict the advantage at each step. So this advantage measures how much better the actual return was compared to the critic's predicted value. We use that information to update the critic, and we use that information when we're training the actor as well. We also compute the temporal difference, or TD error. This gives us an estimate of how off the critic was at predicting the value versus the real thing at any given time step. And then we compute the estimated advantages by walking backward through that rollout. So we go backward through that simulation. We have all that collected data. We can see how well the critic did at guessing the value versus the actual rewards gained, or the discounted rewards gained from any given step. We combine those using this generalized advantage estimate to mix the critic estimations and real rollout rewards. So these are the returns that we get. That's a mixture of those two. They're used as the critic's learning target. So the critic is trying to get better at predicting values from any given state, and this becomes that target. We then flatten all these batches so we can use them in computations. Once we have that information, and you might notice this happening during a rollout where the robot's just kind of moving around, trying to learn how to balance, and it'll just stop and freeze. That's because we've reached the end of the rollout, even though we're mid-episode of a bot balancing, and we're going to perform an update on the actor and critic. So if you're coming from the machine learning world, this will look mostly familiar, where we are simply training or doing a number of iterations training both the actor and critic networks. So we have our mini batches of episode data. We're going to go through those. So you have our batch size that we're going through in the mini batch size chunks. We pass in our observation and actions in order to get the probabilities or log probabilities of the rollout actions from that actor, and then the predicted values from the critic. This is under the new, or the currently being updated policy. We then want to compute the ratios of the action probabilities under the new policy versus those under the old policy. This gives us that ratio, which we are going to use for clipping, which is an important part of PPO. If you remember earlier, we disabled gradient calculation, but we have it re-enabled under this part because we want to do the updates. But in this little section here, we disable it again because we're just doing evaluation. So this is where we approximate the KL divergence. This is essentially a measure of how two different probability distributions are. It's a thing from statistics. A higher clip frac, or percentage of the mini batch that had the ratio that we calculated up here that had been clipped, that tells us how aggressively we are trying to update the actor. So we want to see a little bit of clipping, which means we are actually updating the actor, hopefully in the correct direction. Too much means it's too aggressive, and that means the agent is struggling to figure out how to control the device, or the balance bot in this case. So we will log this to TensorBoard so you get to see a graph of that over time. Similarly, we watch the KL divergence. If it's too large, we just break out of this training loop because we're trying to overshoot the target. We then want to standardize those mini batch advantages that we previously calculated. We then calculate this policy loss, and we're going to clip it down below to prevent too large of a target change, because this loss function becomes our target for when we are trying to update the actor and critic, which you will see in a moment. So first is the value loss. This is the mean squared error between the predicted value and the returns at those time steps. We are using this to determine the difference between how well the critic predicted a value at a given time step versus the actual discounted reward from that time step. So that's what this section is doing. We end up with our value loss down here. We also want to keep track of the measure of entropy, which is another term that describes the measure of action distribution spread, how spread out the action probability distribution is. So with high entropy, the actor is giving us wide distributions. With low entropy, the actor is giving us narrow distribution, which means it's more deterministic and essentially saying that the actor is more confident in those actions to be performed. From here, we compute a single loss, this value, for both the actor and critic networks. It's a combination of the policy loss, the advantages we calculated earlier, the entropy that we just saw up here, and the value loss, the differences between the predicted values and return. So all those come together to create this one loss value that we use as loss functions for both networks when we're trying to do updates. So then we reset to 0, and then we perform backpropagation, which is just a standard function in PyTorch. We then clip the gradients, or clamp them between two different values to prevent the magnitude from being larger than the given max grad norm parameter. Once again, this is just a value you pass into this config that we created earlier. This is preventing the parameters in both the actor and critic from changing by too large of an amount. In my experience, reinforcement learning is very sensitive to small variations in hyperparameters, which means minor variations in those hyperparameters could send the agent off in a wild direction, doing something you didn't intend, overshooting its possible maximums, or just resulting in catastrophic forgetting. By ensuring that the agent, the actor and critic networks in that agent, only take small parameter steps or small parameter changes, we find that it's not liable to overshoot, and you're more likely to converge on good actions that give you good returns. Once we have that backward pass done, we can then apply the gradient descent step, where it just actually updates the parameters inside both agent networks. We then want to log a whole bunch of stuff to the TensorBoard output so we can see what's going on for that particular run. We will talk about what we're seeing here when we look at TensorBoard. We also want to periodically save the model. This is a checkpoint. This allows us to go back to a previous model if one was performing very good, or the best, in a given run, and we can use that for the next phase or use that one to deploy rather than whatever came later. We also want to optionally save the final model, and then we'll print the best model summary from checkpointing. There's also this ability to upload to Hugging Face. This was something that was in the original CleanRL implementation, and I just disabled it here because I'm not using Hugging Face. We will close out of the environments if this module owns them, but if we've passed them in, let the caller deal with them. And we'll also close out of logging to TensorBoard. We then return the training results, which includes the agent, so we can evaluate it and hopefully use it in the next phase or deploy it to our robot if we really like it. And then if you really want to call this as a standalone script, which is how CleanRL was written, it goes ahead and calls the train function that we just looked at. Now that we have our environment and PPO module ready to go, we can start training. Before we do, I want to mention that we will be using a technique called curriculum learning. This is a common approach in reinforcement learning where you train in multiple phases that increase in difficulty. If you just allow the agent to train on the full task, you'll often find that it will use some workaround or cheat that technically accomplishes the goal but misses the intended purpose. If you watched my AI Plays QWOP video from a few years ago, you can see that the agent learned to scoot on the ground rather than learning to actually walk or run. This is a good example of the agent using a workaround to accomplish the goal of go far without learning the intended behavior of running in this case. One way to combat this is by using curriculum learning. For QWOP, I might have initially rewarded the agent when it took a few basic steps before setting up the go far requirement. For our balance bot, we're going to start with two phases. The first is rewarding the simple act of balancing. We don't care if it roams around while doing this, as it's just learning to maintain an upright position. After that, we train again using the same agent, but we start penalizing moving back and forth or turning. This helps the agent ultimately learn the intended behavior. Back in our container, let's close down our environment test. We're going to open up train with PPO curriculum. Don't forget to push Shift-Enter to run through these. We're going to import our standard libraries, import our third-party libraries. We also want to import our custom environment that we created and we've already tested. And we are going to import from that RL folder. That's one up from here. So we need to append workspace software to our path. And we're going to import all of the functions and classes that we need to use from that. We have some global settings here. So we're going to want to run 4 environments in parallel. Remember, only the first one is going to be rendered for us. And then we want to run 500,000 steps, so that's time steps, per environment. So let's Shift-Enter that. We then set up PPO. You see all the hyperparameters we have to configure here. We have 2 hidden layers in our actor and critic networks. Each of those layers will have 16 nodes. So we're starting off with a pretty small neural network for each actor and critic. It's generally a good idea to have your actor and critic be the same or similar architectures. We calculate the total number of time steps for each phase, and this is number of environments times steps per environment. We then specify the number of steps per rollout before performing an update on the actor and critic, number of mini batches, number of epochs to update the actor and critic for each iteration. We have our initial learning rate if we want to lower that over time through annealing. We set our discount factor, how we blend the errors when we're doing the network updates, how we perform clipping to prevent overshooting our targets. We set up how much entropy factors into that total loss calculation. We're not going to actually use it here, but that was part of the original CleanRL, and how much the value loss factors into that loss calculation. These are just setting up some coefficients. Remember, when we mix all of those different factors together to create a single loss value to update our networks, that's how we're controlling it here. Another limit on how the actor and critic parameters can change during an update and how often we want to save a checkpoint. We're going to say every 50 iterations. And if we want to save the final model, which we do, this is where we would normally set our time step to 5 milliseconds, but we're going to set it to 0 so that the environments actually run faster than real time. But then when we deploy the actor, it's as if it was trained for 5 millisecond times from that MJCF file. So this is how we go faster than real time. So let's press Shift-Enter to run that. Here are 2 functions to generate our environments. Notice that we're going to make a number of environments, and the first one, the render mode gets set to human, otherwise there is no rendering. So we're going to run that. This is the first phase where we only want to balance. We're not going to worry about position or rotation. To do that, we set our action and pitch penalty coefficients, and we set the position and yaw penalties to 0. So the agent won't care about maintaining position. It'll try to stay upright, and you'll see it kind of wandering around. That's fine for this phase. I initially tried to do this in one phase rather than separate it apart. The bot really struggled to learn how to stay still and to stay upright. So by breaking it apart into phases, doing what we call curriculum learning, we can train it one little thing at a time, and we shape its behavior toward what we intend rather than hoping it just stumbles upon it randomly. With that, we're going to press Shift-Enter. We're going to start training. You will see our simulation pop up here, and I can control the camera, zoom in and out. You will see the bot falling over a lot, and that's because it's trying random things initially, remember controlling each of the motors, until it starts stumbling upon something where it starts getting better rewards. In other words, how much it's staying upright. So I'm going to go ahead and let that train for a while, and we're going to come back to this once it's done with this phase. With the training done, let's see how it performed in TensorBoard. You'll want to navigate in another tab to localhost 6006. Remember that the container is broadcasting TensorBoard through this opened port. Let's go through each of these. So SPS is steps per second. This is an indication of how many steps in each of the environments was completed for each second. This gives you an idea of how well you're parallelizing the environments. So if you start increasing the number of parallel environments and this value starts to stay the same, that means you've reached your max. So you can see we're hovering around 2,000 steps per second here. We have the episodic length. This essentially gives you how long the robot stayed upright. As we expected, it started to fall a bunch when we first started training. The policy started to figure out something that would keep the robot upright, and then towards the end, the robot would make it to the end of those steps for each episode. So it got too truncated rather than terminating the episode because it fell. Then we have episodic return. This is a total of the amount of rewards received for each episode. This is probably your most important metric because it gives you an indication of how well your agent is performing against your reward function. So once again, it's probably going to start low as the policy is trying random things. It starts to increase. You can see it's got some dips here, and then it starts maximizing rewards towards the end, which is exactly what we want to see. Learning rate shows the learning rate slowly decreasing over time. That's because we enabled annealing. That's fine. We also have mean return. This is a smoothed or average version of episodic returns, which we have up here. This is what's used in our code to determine the best model and what's saved off. So if we come down here to our losses, you might have to drop this category down. We have approximate KL. If you remember from our code, KL divergence measures how different the updated policy is from the old policy, or the one that collected the episode data, also known as the rollout. Large values of this means that the policy is changing too much. So you just want to keep an eye on how well this is performing. ClipFrac is the fraction or ratio of the number of times we had to clip the policy updates. So if you remember, we calculate the ratio of probability of taking an action under the new updated policy over the old policy that collected that data, that rollout. PPO prevents large updates to the actor by limiting this or clipping that ratio. High values of this means that PPO is trying to update the actor too aggressively, and that means you might need to adjust your learning rate. So in the 2% or 4%, that's usually pretty good. If it's going more than that, so you see it pops up here as it's aggressively trying to update the actor, but then it comes back down towards the end, which means that it's settling on a known good policy. So this is okay. We also have entropy, which tells us how random, remember the spread of that action distribution from the actor. In PPO, the actor provides several possibilities, that action distribution, for a wide variety of actions. This often starts very wide, hence large entropy, in the beginning, while the agent is trying new actions to try to figure out what works. As the actor converges, you should see this entropy go down, which means that the actor is settling on a more deterministic probability distribution. So that distribution gets narrower, which means the actions chosen are exploiting known good rewards. So this is what we want to see. We want to see this entropy fall. We then have explained variance. Explained variance, oh, this is interesting. It's supposed to give us a measurement describing how well the critic is predicting the actual returns from the episodes. Because it's an R-squared metric from statistics, 0 basically means the critic is no better than predicting the mean total rewards for all the episodes in a given batch. Negative, as it starts down here, it's worse than that. And we want to see this approach 1. So it looks like there's a bug somewhere in the code because we do see that the agent is working. So if you find that, please let me know. It's just something we're doing calculating this. It trains correctly. It's just how we're logging explained variance. So we will ignore explained variance for now. We also have old approx KL, which is just another way to measure KL divergence. We generally care about this one, the original one, so I would just ignore that one for now. We have policy loss that shows how much the actor is being updated. Large spikes show unstable updates, meaning it's trying to take large gradient steps. This should tend towards 0, which it kind of does at the end. to indicate that the actor has converged on a stable policy. Finally, we have value loss. This is the mean squared error between the critic's predicted values and the actual returns from the episodes. This should tend towards 0 as the critic gets better at predicting actual returns. High values of this means that the critic isn't really learning, and you can see it tend towards 0, so the loss goes down over time as the critic is learning to predict returns better. I find this makes a lot more sense to me than explained variance, and explained variance has a bug in it right now for logging, so we're just going to go with value loss to see how the critic is performing. We're going to go back to our code here. So we're going to switch over to eval mode. We're going to evaluate the robot. And so we're going to run that, and you can watch the robot actually run the agent or the policy that we just learned. So we're not doing any updates to the agent here. It's just running the learned policy. As you can see, it wiggles about the origin, it moves off the origin. That's fine. We're not punishing it for moving and turning, but it is staying upright, which is exactly what we wanted. It should run 3 of those. So I think it's on the 3rd one now. You saw 2 of the resets. In just a moment, it should stop and give us information about those runs here. So there we go. We have our mean return of about 2,000. So if I remember, the eval config is just a copied version of the PPO config, but we changed the time step to be 5 milliseconds, which is why we were able to see this running in real time rather than a sped up version. Let's get that checkpoint directory in case we need it, in case we want to say load a previous agent, and then we're going to export as CSV files. If you want, you can go find those CSV files. You can upload those to something like ChatGPT or Claude and ask it to analyze those graphs, but we just went over how to read those. Now we're going to go into phase 2. We're going to go through each of the environments, and we're going to update it so that the reward functions change. We're now going to add in our penalties for moving off the origin and for spinning about the origin, that yaw coefficient here. So previously those were 0. We're now going to make them 0.001 and 0.1. These are hyperparameters, so feel free to play around with those. I just found that these kind of worked more or less out of the box. So let's just go with those coefficients to penalize moving and spinning. Let's go ahead and train, and it's going to start with that previously trained agent, so it should be standing mostly upright, but it's going to explore, so you might see it start falling over as it starts to explore that. Let's let this train, and we will come back and take a look to see how well it did. Once training is done, let's go over to TensorBoard. You should see 2 sets of lines now, one overlaying the other. So the light blue one for me is phase 2. And if we look here, you can see that parallelization, it's still around 2100, it's fine. The episodic length, you can see where the light blue line, it shows that the robot started tipping about 2/3 of the way through, and then it actually settled back on not tipping, which is what we wanted to see. Similar with episodic returns, as it explored new options, it was tipping over, so these graphs kind of line up here. But then towards the end, the last 500,000 steps or so, it looks like it was maximizing its returns, which is exactly what we want to see. The learning rate followed the same schedule as the previous phase. That's fine. And we can look to see how the updates were performed for the actor and critic networks. So what's interesting here is you can see entropy going down even more as it became more deterministic. We had some spikes in the clipping ratio, but that eventually came down. Explain variance still doesn't work really well. And approximate KL, where was that? So KL divergence, that's trending down. That looks fine. And then the policy loss, what's interesting is that it was negative for a while, but it eventually came close to 0. You can see our range here is pretty small. So this looks pretty good. Oh, and including value loss. What's interesting is that the critic didn't really update a whole lot. It mostly stayed the same, so it was still a useful model for predicting the returns given an observation, but the actor needed to change, and that's what we saw for the rest of this. If we go back to our notebook here, we are going to run this cell that will load the best model from that previous phase. We're going to switch to real-time time steps, so 5 milliseconds, and we're going to run the evaluation. And looks like the bot's not doing anything. You can see it slowly wiggling. The shadow is a giveaway here as it's staying perfectly upright. Remember, this is what we're seeing in simulation. and you saw an episode reset where the bot started to tip a little bit. That was that initial randomized push, and it had no problem balancing itself, and it's not rotating and it's not moving off the origin. This is exactly what we want to see. So once this episode ends, it should give us our mean return here. Hey, that looks good. We are going to export the CSV files, and we're going to close out of the environments. So once that runs, that should close all 4 environments. And I'm going to go ahead and run that export actor to ONNX function so that you can get the ONNX file from just the actor if you want to use that in something else. But in the next episode, we're going to actually turn this into C code, so we won't be using that ONNX file. If you really want to look at that ONNX file, remember that's just the actor, it's not the actor and critic. Go to netron.app, open up your model, go into wherever you are working. So for me, that is in reinforcement learning. Let's go to workspace, software, go to second episode, go to runs. We have the one we just completed. There is the exported actor ONNX file. Open that up and you can see it's a pretty simple neural network. So if we click here, you can see the observation space. We have our batch size. So for one observation, that's 1. We have those 4 elements, pitch, pitch rate, left motor, right motor encoders. The output, batch size of 1, 2, left motor, right motor torques. You can see the 2 hidden layers here. So those are 16 nodes in that first hidden layer. We're using a hyperbolic tangent activation function. We've got another hidden layer that is 16 nodes, another hyperbolic tangent activation function, and then our output layer that gives us the 2 values for the left and right motors. At this point, we have an agent that balances pretty well. In the next episode, we will take just the actor network from the agent and deploy it to our actual robot. We'll explore the sim to real gap. As you'll see, the robot does not perform nearly as well in the real world with this initial policy. Stay tuned.